Hi, thank you so much for joining us today. We're really excited to have you. So you've done and are doing fascinating work, kind of building machines that can learn and create models of the world, partly inspired by the way humans build models of the world. And you recently co-organized a workshop at ICML on object-oriented learning. Could you talk a little bit about that and your work there?
Sure. Yeah. I guess I'll start just by saying thank you so much for inviting me to do this interview. I'm really honored for the invitation and to be here to talk to you. So I think one of my sort of philosophies of like the research that I do and that I'm like is that I think humans have evolved to be really, we can very flexibly reason about the world. We can, imagine the world in all sorts of like new configurations and like new operations on the world. And we have like evolution has basically imbued us with strong inductive biases that enable us to do those types of, mental operations and reasoning. And one of those inductive biases that we know from like developmental psychology and lots of work in cognitive science is sort of a expectation that the world is made up of discrete entities like objects, right? And that may be things like physical objects. It could also be other types of discretizations. So like, you can have temporal objects, which maybe are things like events or even just like concepts in general are like sort of like mental objects, right? But I think like the fact that we are constantly doing this, carving up the world into these discrete entities is really, really important. And so part of, the reason that I wanted to help co-organize this workshop on object-oriented learning and in general, like a lot of the themes in my research are resting on this idea that objects should really be, I think, front and center in a lot of the research that we're doing.
And what kind of new modeling paradigms do you think are needed to kind of get this kind of discretization of objects into machines? I know you do really cool work on graph representation learning. Does that relate to this idea?
Yeah, definitely. Well, I think there's, excuse me, there's sort of like, there's two stages of it, or at least two stages, maybe three, maybe more. One is, sort of parsing the world into a structured representation. So that's taking in all of this unstructured data, like visual perception, proprioception, auditory data, all of these like multimodal, sensory modalities. These are, it's like a stream of incoming data that's not very structured in and of itself. And our cognition as humans, we turn that into these structured mental representations. And so my work has been less focused on this like first part of transforming the like unstructured data to structured data. So it's a very important component. Though arguably the object-oriented reasoning workshop was focused more on that component. But for me, the stuff that I focused mostly on is, say, assuming you have some sort of structured representation to start with, what can you do with it, and how can you leverage that to do better forms of reasoning and generalize better and sort of, work our way towards having agents which are able to achieve some notion of what we sometimes call like combinatorial generalization, where the idea is that you learn about a lot of different things in the world, and then you're able to know how those things combine in new and novel ways and generalize to combinatorial different number of situations.
And is there a particular human ability that you find most exciting or kind of most challenging to model in machines and kind of in this setting?
Yeah, so I think sort of exactly what I just said is this capacity for combinatorial generalization, I think is something we really don't quite know how to do like at all. Like, so I give there's one example that I really like that I give in a lot of talks these days, which is this example of blueberry Earth. So there was at one point in time, someone asked on Stack Overflow the question, what would happen if you replaced the Earth with a bunch of blueberries, or closely packed blueberries the size of the Earth? And then, so what would happen if we did that? And then someone actually went and like wrote a paper like applying principles of physics to sort of like run this thought experiment to its logical conclusion. And they go and they talk about, oh, well, it's like similar to, this particular type of planet, and you know, who knows if it's like that is actually what would happen. I mean, that's obviously like a scenario that's never going to happen. So it's hard to know if the physics would actually be applied in that way. But I think it's really remarkable that we have the ability to even conceive of that scenario in the first place, and then like come up with like a plausible explanation for what would happen, right? And that's not something that you see any AI system really being able to do. And like either you have like, I guess, current like deep learning systems don't generalize that well. So like if you try to like ask them to think about something outside of their training set or some combination of things outside of their training set, they're not really able to do that. And I think even like other, you know, there's a lot of proposals for things like, oh, well, maybe, you know, we have to rely on representations that are more structured, like graphs, like you mentioned the graph neural networks, or things like programs and stuff like that. And I think that those are very promising directions, but I think we, like, you know, despite like the work that's going on in those areas, we still haven't seen the type of like generalization and creativity and imagination that is sort of exhibited in this Blueberry Earth example. And so that's what I sort of see as like the moonshot.
Kind of going off of that in the imaginative kind of like Blueberry World example, you recently wrote a fascinating paper on mental simulation and imagination that I really loved. It was really inspirational to me. Could you talk a little bit about kind of some more on your work imbuing models with simulation or imagination abilities in some way? I know you did work with Josh Tenenbaum earlier kind of on simulation of like block towers and things like that. Could you talk a little bit about what you see going forwards related to machine versus human imagination or simulation abilities?
Sure, yeah. So I think, yeah, so I'm glad you liked the paper, first of all. So I see, so my research trajectory has sort of been like, yeah, so as you mentioned, I started working with Josh many years ago at MIT and studying how mental simulation works in humans, specifically how like we use mental simulation to reason about physical processes. And then I went on to do my PhD, continuing to study mental simulation, often in the context of physical dynamics and physical reasoning. But sort of with the question of like what is the purpose of having a mental simulation? Like what can we use it for, and how can we make smart decisions about the way that we use our mental simulations? Because you don't want to sit there all day running simulations to like come up with a prediction of what's going to happen. You want to make decisions quickly, right? But so now that I'm sort of, you know, moved, so my PhD was in psychology, and now I've moved back into the direction of AI, and I think that like paying attention to the ways that humans use their mental simulations, for example, in these contexts of intuitive physics, but also in other cases, like how we use mental simulation in the context of creativity, in like game playing, in scientific reasoning, like in all of these different areas, I think is really, it can really provide a lot of inspiration for like what's missing in machine learning models or machine learning agents that use models of the world. I think model-based RL is a really interesting area of research in machine learning because it sort of combines this idea of having a model of the world, so building a predictive model of the world, and then combining it with the ability to make better decisions. And that's, I think, like a really interesting sort of like hybrid style of architecture that is a little bit different from either just like purely predictive models. So, you know, say like things like a lot of the stuff in computer vision or in language, like really interesting research, but is purely predictive and not really being used to leverage interventions on the world, right? It's like, I'm going to just predict like, you know, the next frame in the video or whatever. And then also like similarly in model-free RL isn't really about building predictive models of the world. It's just about making good decisions. And so I think the intersection of those things is really interesting. But then when you compare model-based RL to where we are with humans, how humans use their models of the world, there's really quite a large gap. And so for my research, I find it, you know, I try to basically look at like what are the things that we know about how humans use their models of the world, both the types of things that I researched before in terms of like intuitive physics and during my PhD, and of course all of the surrounding literature from this whole field, and then trying to like distill that into some insights that we can then try to build into our AI agents.
You also recently wrote a paper kind of calling for applying Mars levels to machine learning. Could you talk a little bit about your work there and why you think that could be an important conceptual framework for the field?
Yeah, so I guess that paper sort of like was born out of like a different, it's interesting because it's like, it's another way of taking ideas from cognitive science and applying them to machine learning, though it sort of came from a completely different like direction and inspiration, which is that like, I spent a lot of time like reading various machine learning debates on Twitter and getting kind of frustrated that it sometimes seemed like people were like talking about the same thing, but in very different ways. And then we're not really always, it seemed like they weren't always necessarily understanding each other. And you see often the same thing in cognitive science as well, or at least historically that's been the case. I think sometimes it's also still the case, but then the reason for it is often that people are talking at different levels of analysis of thinking like, am I talking about like how the system should function, like what is its goal, or am I talking about like what are the components that are used to build that system, or like so there's various sort of like like lenses that you can view a computational system through. And that, I think, if you and someone else are viewing the same thing through two different lenses and then trying to talk about it, you may not necessarily have a productive conversation. And so the levels of analysis I see as being basically a way to determine whether you have the same lens as someone else, and then if not, arrive on the same lens so that you can then have a more productive conversation about it. So I guess for those who might not know, I assume you being in Josh's lab, you probably know what the levels are, but for those who don't know, like the levels of analysis are a conceptual framework that comes from neuroscience and cognitive science, from David Marr and Tommaso Poggio as well. The idea is that if you're studying a computational system, say like the human mind, how do you understand it? Well, you can understand it from different levels of analysis. You could understand at the computational level, what is the goal of the system? So what problem is that system, like the mind, trying to solve? At the algorithmic level, you can understand it in terms of what are the actual like algorithms that it's that are producing its behavior, and what are the representations that those algorithms are operating over. And then at the implementation level, how is that system actually physically realized? And you can basically, and so, it's sort of natural to talk about that in the context of human cognition, because you can say like, oh, okay, well, like what's the purpose of like the visual system, or like you want to analyze the visual system. You can say, okay, well, the computational level goal is like obviously to convert like, light into things like mental representations that can then be acted upon, and then you can say, okay, well, how does it do that? Like, what are the algorithms that support that, and then how is that implemented neurally? But you can do the same thing in machine learning. It looks a little bit different, but you can say the example that one of the examples that we used in the paper was like looking at DQN, which is a reinforcement learning algorithm that DeepMind trained to play Atari. And you could say, okay, like at the computational level, what is the goal of DQN? Well, maybe it's to, it's the same as the goal of any reinforcement learning system. It's to maximize scalar reward, which is, given as an external feedback signal. And then you can say, okay, so that's like the computational level goal. And then the way you might like achieve that computational level goal is by, say, solving the Bellman equation or the Bellman optimality equation. And then there are various like algorithms that do that, right? So one of those algorithms is like Q-learning, but you could also imagine using an algorithm like policy gradient or something. And you can implement those algorithms using like deep learning and function approximation. And so in that way, you can sort of break down your understanding of this algorithm along these three levels. And then that is useful because if you say wanted to like critique a particular algorithm like DQN, like say, oh, DQN doesn't work well enough because or it's insufficient because it doesn't have a notion of like objects, explicit objects, right? Well, then is that critique happening at which level of analysis? Are you saying that the computational level of like maximizing scalar reward is like the wrong goal for the system to have? Or are you talking about at the algorithmic level that like the algorithm should have some notion of objects in it, right? It's not clear from just asking or just giving that critique which of those two things you mean. And so the levels can sort of make that clear.
And kind of, it seems like you've gone between and kind of work across machine learning and cognitive science. Has anything surprised you about the dialogue between kind of the different communities, whether they're getting closer together or pulling apart, or if there's kind of a sub area that you think is ripe for more conversation?
Yeah, so I think the two fields have sort of the two fields have like a really long and rich history, stemming from like at least like around like 1930, but like going probably further. I mean, they weren't called machine learning and cognitive science at the time, but like these ideas of like building machines that can be smart and understanding how humans work obviously are two very old questions. And so over the years, they've sort of naturally grown further apart and like come close together. My cat has decided to join for the interview too. He can go on the ground though. And so they've naturally sort of like drifted apart at times and come closer together at times, and drifted apart and come closer together. And I think I would say like over the last like I don't know. I think since like the beginning of the deep learning revolution, or like the resurgence of deep learning since 2013 or so, I think that the fields have drifted a little bit further apart. Like there aren't that many cognitive scientists who are employing deep learning methods, and there aren't that many deep learning researchers that are paying like close attention to cognitive science. But I think that is starting to change. I think they're starting to come back together now. As I think in deep learning, there's been for a while sort of this philosophy of like, oh, if we just have like enough data and we scale up our models enough, that like that will be sufficient to reaching general intelligence. And I think a lot of people in the field are starting to question that belief, and then they're turning to other areas that might provide potential solutions, cognitive science being one of them. And so I see them as sort of starting to come together a little bit more now. And I think maybe like the main thing to realize for people coming from machine learning would be that like cognitive scientists don't have all the answers either. If we did, then we would like, there's plenty of cognitive scientists who are also interested in AI. And so if we had the answers, we would have built, general purpose AI already, I think. But more to say that like, cognitive scientists have been asking questions about how human cognition and other forms of cognition too, like animal cognition, works for a very, very long time. And we've asked very nuanced questions about it. And that it's important to like engage in those questions and the answers to them. And that like, you're not going to find like a hard and fast answer, but that you may come up with new ideas and new inspiration from and sort of a more, I guess, a more nuanced view of how like particular aspects of cognition might work by looking at those fields of research. And I think similarly, like cognitive scientists shouldn't expect that like artificial intelligence researchers have exactly the algorithm that will work to model the problem that they're interested in. I've also had, conversations with people who are like, oh, like I have this this behavior that I want to model or whatever. Like, how would you like do that in machine learning? I'm like, I have no idea. So because the things that cognitive scientists care about are really complex, and it's again this is like the other side of the same coin, right? If we had the algorithms that could model those things, then we would have solved AI. So, but I think that means that there's like so much space for the two fields to collaborate and learn from each other, because like each of them has things that the other field wants and can benefit from. So it's exciting to see that I think more people are getting interested in it now.
Awesome. And what excites you most about your research going forwards?
I think it's sort of what we were talking about, like at the beginning, is like figuring out like what are the like what exactly are these like types of structured representations and the computations that operate over them that allow us to like reason in this like sort of combinatorial way. And I think I think that there's many like facets to the answer to that question, or like to the question of how does that work. But I think one of the things that I've been particularly interested in recently is in thinking of what are the operations themselves that need to operate over those structured representations. So like there's a lot of work that goes on in terms of like building models of the world and figuring out how those models should be structured. But then even once you have the model, you have to use it in like a productive way, right? And for many problems in the world, like just having a model and sort of like querying that model extensively isn't going to get you very far. So I think, I mean, being at DeepMind, maybe I'm like influenced by the work of a lot of my colleagues, but I think Go is actually like a really good example of this, where to learn how to play Go, like if you just try to train like your standard model-free algorithm, it doesn't work that well. And if you just build a model of the world, or if you just built a model of the game of Go and then tried to like run simulations from that model, that also isn't going to be sufficient, right? You have to have this like tightly integrated system that has a model and makes good decisions with that model and queries that model in an effective way. And then I think Go is, of course, in a lot of ways easier than many of the real world problems that we face. But I think it's because of that, it's such a good example that like, even here's a problem that's like, it's very well defined. Like, we can know exactly what the rules are. The rules are deterministic. It's fully observed, right? It's discrete. When you move away from those assumptions, then I feel like it's even more true that like you have to have a good model, but you also have to have a way of using that model effectively. And so the stuff that I've been most interested in recently is sort of examining that question of like, how do you most effectively make use of your model beyond just having it in the first place?
Fascinating. And kind of shifting gears a little bit, you've also done work on Jupyter notebooks and reproducibility. Could you talk a little bit about your work there, kind of why you think that's important?
Sure, yeah. So, well, I should say unfortunately, I'm not quite as involved in Jupyter anymore as I used to be. It's too many, I guess, obligations to, but I still, it's something that like is very important to me. And I've always kind of had a strong feeling that like open source and sharing of knowledge is really important. And I guess maybe that comes from having done my undergrad at MIT. MIT has a very strong like open source culture. But when I went to grad school, I wanted to contribute to an open source project, and so I started contributing to Jupyter, and that's sort of how I got involved there. And part of that is like I see the Jupyter notebook, as being like a really nice tool for being able to explore your ideas and then share them with other people. And it's something that can also be, really facilitate things like reproducibility, which is particularly important in empirical fields like machine learning or psychology, et cetera. And so, yeah, so the work that I did in Jupyter is sort of, I guess, sort of like a little bit of two branches of it. So the main branch was I worked on using Jupyter in educational contexts for creating assignments for classes, which is a little bit less about reproducibility, though I think was the reason why we created that tool. NBGrader is what it's called, was to help both because the notebook format is really good in an educational context, because you can sort of like have the instructions and an explanation of like the particular assignment directly in line with the rest of the code, but also because then it can help students like gain the experience of working with these tools, which are then widely used elsewhere outside of the classroom, right? And then I think sort of the other like part that I worked on less extensively than the educational side, but was in terms of using the notebooks in a very reproducible context, and like having them. I had a very like, and I still am very like strongly like convinced that, for example, like when you create a figure for your paper, you should be able to like rerun the script and get exactly the figure out. Like you like none of this like putting the figure into Illustrator and then like modifying it there. Like you should do it all programmatically in code, which is a strong belief. But it's nice because then like you need to modify something about your figure. Like maybe you found an error and you have to like replot all the data. Now you don't have to do this manual step anymore. You just like rerun the script that creates your figure. And then the notebook you can have the figures output inline. And so it's nice to have a way to sort of like programmatically run all the notebooks that you have that create your figures and do your data processing and stuff. And so I also worked on tools for like helping reproducibility along those lines too. And in general, the idea of like having the notebook that facilitates reproducibility for both for yourself and for other people, sort of in like a almost more of like a communicative context, I think is really important. So, you know, I'm not necessarily like committed to the idea of like exact reproducibility in terms of like, you know, oh, you run this code and you get exactly the same decimal output. That's not always feasible, especially like with different types of hardware that might like introduce small forms of noise. Sometimes you can't control all of the code that you have access to, and like maybe you rely on an external library that's stochastic or something. So you might not always necessarily be able to get exact reproducibility. But I think the more important concept is like replicability, which is being able to sort of like re-implement something and get it to work and sort of understand the ideas behind that like algorithm or piece of code, and putting the code in a format like the notebook that you can then run and see all of the outputs. Like even if you don't end up, you know, getting like exactly down to the decimal point the same results, you can see the logic of the program and you can understand like how it's meant to be implemented and how the analysis is meant to go. And I think being able to observe those things as a researcher or communicate them to other people is really, really important for scientific progress.
And you've kind of talked about this a little bit throughout, but can you talk some more about your trajectory? How did you first get interested in machine learning and even computer science, and then kind of also merge to cognitive science?
Sure, yeah. So so before I started working in Josh's lab, I was when I started working in Josh's lab, I should say, I guess, I was an undergrad at MIT studying computer science, and I was very interested in artificial intelligence, and I had been taking various classes on AI, and I also had like a previous sort of like research Europe undergraduate research opportunity, working on, you know, some like robotics type stuff. But I kind of was, I was a little bit disillusioned with the state of the field at the time, which looked really different than it does today, because that was before, that was like I think I joined Josh's lab in 2010. So that was, you know, before deep learning sort of took everything over. And, but I felt like at least, based on the stuff that I was seeing, that they didn't feel like there was a strong connection to how we think about things to me. But then I was like, oh, like I was always introspecting and thinking about myself. And then I'm like, but I don't really know how that works. And so then I was like, I think it would be really important for me to look at how humans think about things and then use that for AI. And so I started looking for like positions in the brain and cognitive sciences department, and I found Josh's lab, and I was like, oh, this looks like exactly what I want. So I cold emailed Josh, and he was nice enough to give me an opportunity to work with him. And so I started working in his lab, and I started working on the sort of like intuitive physics, physical simulation stuff that we were talking about earlier. And then as I was working on that, I sort of got more and more enamored with cognitive science itself, sort of like independent of AI. And I really kind of, for a while, was working more just like in pure cognitive science. And then, and that's sort of like what, you know, made me want to go to grad school in psychology rather than computer science. And so, yeah, I went to grad school at UC Berkeley, where I worked with Griffiths. And again, still doing like computational cognitive modeling, very much more like on the psychology side of things. But then towards the end of my PhD, I started getting interested in AI again. I started doing some collaborations with people in robotics, and I really enjoyed that. And then I did an internship at DeepMind in 2016, actually working with Peter Battaglia, who I worked with at MIT. He sort of emailed me and he was like, "Oh, you should consider applying for an internship." And so I applied and I got it. And that was a really great experience, and it totally like made me feel like, oh yeah, I want to get back into that more. And so yeah, that's sort of, since then, after finishing my PhD, I decided to join again full time, and now I'm sort of like full time doing AI stuff again. But still I still have a lot of interest in my cognitive science background and roots. Like I still feel like there's so much more to be learned from like what we know about how humans think about things, and that it's really important to pay attention to that, especially if we want to try to solve AI on a reasonable timescale. So I think, again, I sort of mentioned there's like often a feeling in machine learning that like if we just have enough data and big enough models, then we will get to something that looks intelligent like humans. And I think that is true to some degree. I mean, because I think humans are kind of like a proof in principle of that. Evolution produced us, right? It took a really long time and a lot of like data or real world experience, but we exist today, right? But I don't think that we want to replicate that evolutionary timescale. I think we want to try to achieve AI on a much shorter timescale. And but then to do that, I think that for me, the most promising strategy is to look at the examples of intelligent creatures that already exist and figure out like how did evolution like produce us, and can we try to distill that bit of knowledge to sort of repeat that process more quickly.
It's really fascinating. So kind of final question, do you have any advice for students who might be interested in machine learning, or maybe intersection of machine learning and cognitive science? High schoolers, early grad students, undergrads?
Yeah, so I would definitely say I think especially for like undergrads and grad students is take classes in both fields, and that will and try to, I think, spend time with like other students that are in both fields. I think just being exposed to the ideas in like in a serious way is like a really important starting point. And then I think from there will be sort of natural like ways to get involved in other projects. So maybe if you're a student in computer science, try to collaborate with cognitive scientists or neuroscientists on a project, and vice versa. If you're in cognitive science, try to collaborate with computer scientists on a project. And I think in the course of doing that, you will sort of force you to really learn a lot about the other field. And I would say that, so like, don't necessarily feel like you have to stick to one field always or the other. Like, it's okay to sort of like go and spend some time, focusing mostly on like the AI side of things, and then go spend some time like focus on the cognitive science side of things, and then like go back. And I think that like it's important not to stretch yourself too thin, and it's okay to like, move from, like spend different parts of your educational experience like learning about different fields and different approaches and different ways of thinking about things. Yeah, I think that that's kind of like the way that my trajectory ended up going. Like I first was really focused on AI, and then I became really focused on cognitive science, and then I became really focused on AI again. And I think that actually was good because it allowed me to go really deep into like the particular areas and fields that I was working on. Whereas if I had tried to kind of always do both at the same time, I think maybe would have prevented me from going deep enough into either field. So.
That's awesome. Thank you so much for joining us. Really fascinating talking to you. Really appreciate you taking the time out of your day.
Yeah, thank you so much for having me again. Yeah, thanks. I really enjoyed chatting as well.